Hi everyone, welcome to Snetly. In this video, we are going to discuss about real-time speed control of sensor-based PMSM motor. We will see both module level design as well as configure PMSM motor and voltage source inverter with Snetly physically. Let's go into the hardware unit of Snetly. This is the front view where you connect your digital IOs and digital output. This part will be your analog signal where you will connect your voltage and current waveform, and this part will be your high switching frequency PWM area. This will be the interfacing of Ethernet, mouse, keyboard and the power switch on off, and this pin will be your digital input section where you will connect the motor feedback, and this will be your digital output area where we will connect the voltage source inverter power module. From the motor we will get three signal A, B, Z. Totally from the motor we will get 5 pin plus 5 volt and the ground signal with the 3 input signals. Just to connect, we are connecting it. This pin configuration will be internally available in the software so that you can view the layout of the front view. Each and every pin configuration will be provided. And secondly, we are going to connect the digital output area where you will get totally 6 digital PWM. We will connect to the normal 3-phase voltage source inverter power module. From the hardware unit of Snetly, we will directly connect to the hardware unit. Just connecting the cables. Our digital output pins will be from 0 to 5 volt range. You can connect with any power module which you have, and our input also 5 volt level. Now I am connecting the motor feedback, respectively RYB. I am seriously connecting current sensor for the measurement of motor current waveform. If you want your voltage waveform to read, you can connect those pins also. I am just connecting the 3-phase current, 3-phase motor connection. And this is a normal 3-phase voltage source power module. We need to give a supply from the auto transformer. I am just connecting a single phase auto transformer to the power module. The power module configuration maximum you can go up to 200 volt VDC. At first, we are going to develop module level design for open loop control of PMSM motor. This type of motor runs based on the motor feedback, but in a stationary condition we won't get any position sensor feedback. So to create the motor to run, we are going to run it in manual mode. Just I am assuming the sawtooth waveform as a motor rotor angle. So I am keeping the minimum value 0 and the maximum value 6.28 and the frequency to minimum value 8 Hz. These values are nothing but the rotor angle which gets from 0 to 360 degree. In terms of radian we have applied here 0 to 6.28. Just view the output with internal DSO. Connecting the output of sawtooth to the DSO. Make unused channel to be turned off for clear view of image. Just click on run button to view the waveform. Here you can see your sawtooth output and the value from 0 to 6.28 in a continuous sequence. Let's now take the scientific processor. In scientific processor, we are going to create a sine waveform, which is a reference signal to create a PWM. This sine value will be based on the rotor feedback. So based on the rotor angle, we will get the sine waveform. Here D0 will be input to the sine. Output will be connected to Q0. Just to create a builder and apply. Back to schematic. Now connect the output of sawtooth to the processor input. From the processor output, connect it to the DSO to view the waveform. In DSO, we have connected both the input, your rotor angle, as well as based on the rotor angle, we are creating a sinusoidal waveform. You can observe in the waveform. Here the sine starts from the 0 degree of your rotor angle and ends in the 360 degree of rotor angle, one cycle. From the waveform, you can observe your sine comparing with your rotor angle. It starts from 0 degree and ends in 360 with the value of 6.28 in radian terms. Here you see the waveform of sine will be fixed amplitude. In order to we get the variable output, I am just going to multiply with the constant value. So I am going to take another input D1, where we will multiply with the sound output, sine wave output. After creating a system, just click build all and apply and back to schematic. Now we need to give the input to D1. Here I am going to get a variable output of sine amplitude. So I am using a knob. Internal of knob, we need to configure the minimum maximum value of sine amplitude. Here we kept the maximum value 0.97 and the minimum value 0.1. Apply register value, back to schematic. Now connect the output of knob to the D1 input of processor. Just click on the run button. Now you can see that waveform is in minimum value since the amplitude is in 0.1. By changing the value of knob, your amplitude of sine will be vary. In order to get the variable duty cycle, I am just giving a variable input. To run a 3-phase PMSM motor, we need 3 sine reference with a phase shift of 120 degree. So our next step will be to create a 3-phase sine from the single rotor angle. to take math module and one more sine block for we need totally 3 sine for 3 phase. And each sine amplitude will be variable, so I am going to multiply with the external input of d1 to get a variable amplitude for each sine. And we are giving the output to q1 and q2 for other phases. Just connect the net similar to the first one. We have connected the nets. Now we need the value of second sine and the third sine. From the first sine we will give plus 120 degree and minus 120 degree for other phases in order to get the phase shift. And the value we are given in the constant in terms of radian of sine 120 plus 120 and minus 120 value. This value should be added up with the reference rotor angle. Here the D0 will be your rotor angle output, and Q0, Q1, Q2 will be R phase, Y phase, B phase sine wave, and D1 will be your knob value in order to get the variable amplitude of sine. And the constant values are nothing but the radian value of sine plus 120 and sine minus 120 value. After creating the block, build all and back to schematic. Connect the output of processor to the DSO to view the waveform. Click on run button. After applying the knob value, you can see the variation in your sine output. And here you get the 3-phase sine output with a phase shift of 120 degree. These 3 sine will be used as a reference signal to create a PWM. And our next step will be we need to compare these 3 reference with a single carrier signal. For carrier signal, we are going to take a triangle from the Snetly library window, waveform sources, triangle, and configure the value for triangle. Internal configuration 1, if you are going for external, assign as a 0, and minimum will be minus 1 and maximum will be 1, and the triangle switching frequency will be 10 kHz. We need to compare the signal, so I need a comparator. I am taking a 4-channel comparator. Q0 will be your R phase signal, will be compared with a triangle in A1 and B1. Similar like Q1 and Q2. for other phases Y and B. From the comparator output we will get 6 digital PWM output, which will be a sine PWM output. While connecting the sine PWM output to the external hardware unit, we need a dead time controller, and the dead time value will be chosen based on the hardware used. Just connect all the nets and configure the dead time value from minimum 1 microsecond to maximum 1000 microsecond. Here we are assigned as 1 microsecond for our hardware unit. To view the output, I am taking a logic analyzer. The output of dead time controller will directly connected to the hardware unit, where hardware unit will be your voltage source inverter power module. To view the waveform, just click on run button. To get a variable duty cycle, just change the value of your knob, you will get the variable duty control. Let's go into the overview. First thing, we need to know the rotor angle. Based on the rotor angle, we need to create a 3 reference sine with a phase shift of 120 degree, which has been developed in the processor. So in order to get a variable output, I am just used a knob to control the amplitude of sine, and these three reference signal need to be compared with a comparator. These 3 reference signal need to be compared with a carrier signal. From the comparator output, we are using a dead time in order to overcome the overshoot in a hardware part. Now let us take the digital input. This digital input nothing but the motor positional feedback which we get from the encoder. From the encoder we usually get 3 signal A, B, Z will be connected to the hardware unit of Snetly. From there we will get the signals in the pin configuration 1, 2, 3, and 1 will be your A signal, and 2 will be your B signal, and 3 will be your Z signal. And just connecting to the filters. You can use any one signal for speed measurement. For speed measurement, you just need to know the value of your PPR count of your encoders. Here I am using Z signal, nothing but the index signal. You will get 1 pulse per revolution. So I have assigned as 1 in the configuration window, and the output of RPM you can view in the display point. I am going to take on processor. This processor used for calculation of PPR count from the motor feedback. In processor we are going to create a script programming to calculate the pulse per revolution of A signal In legacy processor, we are going to calculate number of PPR present in the encoder. From encoder, usually we get 3 signal, pulse A, pulse B and Z index pulse. Here we are considering 2 signal. One will be your D0 and D2. D0 will be stores the value of pulse A signal and D2 will be stores the value of index signal. From each signal we are detecting positive level edge detection and stores in the value of registers. RA1 will store the value of previous pulse A signal and RA2 will store the value of positive edge level detection of pulse A and RA4 will store the positive edge detection of index signal, and we will calculate a number of pulse A present in 1 cycles, which will count the number of PPR, and we will get the output in Q1, Q2, Q3. Q1 will give the output of positive edge detection of A pulse and Q2 will give the positive edge detection of index signal, and Q3 we will get number of PPR count present in the encoder. We are connecting the glitch filter output to the processor input to the D0 and D2. D0 will be A signal from the encoder and D2 will be index signal from the encoder, and we are getting the PPR at Q4. We are using display to measure the number of PPR present in the encoder. In this way we can calculate number of PPR present in the encoder. And we can measure the waveform with the help of logic analyzer. And we are connecting the processor output to the logic analyzer for edge detection and number of PPR count. We are measuring with the help of display available in the software tool. And we are going to connect the feedback output to creation of your reference signal into the processor scientific processor type 1 module. In the scientific processor type 1, we have created 2 steps. One, manually creation of rotor angle, and other one will be based on the digital feedback. We are creating the reference signal. From this model level design, you can understand that we are getting 3 signal from the motor feedback A, B, Z. You can use any one signal for the speed measurement. I am here using Z pulse, 1 pulse per revolution. Based on the pulse per revolution, it will calculate the RPM in the pulse to speed measurement block. And I am using a glitch filter. In case of any noises from the signal, it will be filtered out. And the processor here we used for calculation of PPR count which will be provided in the encoder signals. To view the RPM, I am going to use a display, and you can calculate your PPR in the display. The logic analyzer used for analyzing of your digital input feedbacks, and the knob is used for the variable amplitude control. You are out with nothing but the rotor angle, which we seen in previous case 0 to 6.28, and in scientific processor we have developed 3 sine wave with a reference of rotor angle. Here we are going to run into condition for a initial based on the system time. First we are going to run manually with the help of rotor angle. After we get the feedback from the motor, we will run it based on the rotor feedback. That is the condition we are given in the switching state 0 and 1. When it is 0, it will run on the based on system time. After switching to 1, it will run based on the rotor position feedback. Here you can see that your digital output has been connected to the direct digital output pin of hardware unit. The specialty of Snetly will be there is no code composer, module level design, which will be directly used in the real time controls. Here I am just giving the auto transformer input, and you can see your DC bus in the voltmeter reading. I am just giving minimum volt. Since we are running it in manual creation of rotor angle, I am just applying 50 volt DC link. Just click on run button in the Snetly software tool. While clicking on the run button, you can see the waveform of your A signal and the number of edge detection you get in the A signal, and the rotor angle is been shown in the DSO, and digital output in the logic analyzer area. You can view your waveform as well as the motor starts rotating. Now you can adjust your auto transformer, and you can go with maximum rated voltage. Here the maximum rated we are going up to 200 just for running the motor condition. Just changing the amplitude, you can see that the motor speed varies and decrease, and you can see your PPR count of the encoder will be 2500 PPR per pulse per revolution we are getting from the A signal. By simply varying the auto transformer to maximum 200 volt DC, and by changing the amplitude of sine, you can see the maximum rated go to 3000 rpm, 2900 something, which is the motor maximum will be 3000 rpm. Just for duty cycle control, I am using this knob. Based on the duty cycle, we will get the respective output voltage in the voltage source inverter module. Based on that, the motor speed will be increase and decrease on. This is a simple open loop control of PMSM motor. Then go with the minimum of VDC, and you can observe your speed, your motor running at high speed and low speed. With the help of displays, you can measure the speed measurement. In next video, we will discuss about closed loop speed control of PMSM motor. Thanks for watching.